and I'm going to be presenting on my project titled Dimer Models as Models of Majorana Fermions, supervised by Professor Denjo O'Connor. So just to give a brief overview of what I'm going to be talking about today, I'm going to try and keep the talk as self-contained as possible. So I'm going to start off with the background about what is a dimer and why do we care about them, I suppose. And then working through dimer models on different lattices, such as the hexagonal lattice, moving on to making that non-bipartite, which I'll explain in a couple of minutes. Then about the dimer model on the triangular lattice, a brief part on what happens when we introduce like a defect into these lattices, and then finish off with just a conclusion then. So background. So what is a dimer? So a dimer can be thought of as a polymer with only two atoms. So if you have two atoms, they're bonded together, that's essentially what a dimer is. If you're thinking of it from kind of chemistry perspective. More mathematically then, a dimer covering is a way of arranging pairs of adjacent vertices or sites on a graph or lattice, such that each vertex is covered by exactly one dimer and there's no overlaps in that. So yeah, as you can see, I've given a small example of, say, a 2x2 graph. There's two different dimer coverings on this, one where they're both arranged like that, and one where they're both arranged vertically then as well. And what also says there's a one-to-one mapping between this graph picture and its dual, which is obtained by replacing vertices with faces and crossing edges perpendicular. So what do I mean by that? This is a simple example of an 8x8 bipartite square grid and its dual, which is just a chessboard type of tiling. So, okay, then question then for people is, how many different covers are there of these dimer coverings for an 8x8 chessboard? So does anyone have any ideas how many ways you can cover an 8x8 chessboard with dimers?
At least two.
That's true, yeah.
400.
400, okay. Anyone else? Okay, so it's not quite 400 and it's definitely not two. So you can count for a 2x2 chessboard, it is in fact two. But when you move to slightly larger ones, it blows up very quickly. So there's just under 13 million coverings for an 8x8 chessboard. So obviously it's very difficult to count these, which is, yeah, I'll come back to how we get around that counting issue in a minute. But going back to the graph sort of picture, so we can think of an edge E between these vertices as a bond between particles, as I was saying. So if we associate a bond energy denoted by epsilon sub E to each of these edges, then we can count the total energy of a dimer configuration by just summing over these energies. Fairly straightforward. Then the probability of observing one of these dimer configurations is given by usual Boltzmann statistics. So you can define the canonical partition function in the usual fashion by summing over the activities of these dimer configurations, and then the probability is given by the following. Yeah, so as was shown before, it's not practical to go and just start laying dominoes on a chessboard to count these. So we use what's known as Castellan's theorem to compute the partition function for this. So Castellan's theorem then, the key is to assign a Castellan orientation to the graph, such that, so you give a direction to each edge on the graph gamma, so that each face of the graph has an odd number of edges oriented clockwise. So if you were to product in a counterclockwise direction over them, you should be ending up with the minus sign. So if you're traveling in the direction of where a vertex is pointing, or where an edge is pointing, then that corresponds to a +1. If it's going in the opposite direction, it corresponds to a -1. So you should always, if you travel around any face in your graph, you should end up with -1 when you product over all. So one can then construct a Castellan matrix K for where the entrance ij. So a Castellan matrix is basically a signed and weighted adjacency matrix for anyone who's familiar with graph theory. such that each entry is given the weights being the activity of these bonds, so e to the minus beta epsilon, and the signing convention is as follows. So then we can compute the partition function by getting the Pfaffian of this Castellan matrix. So Pfaffian is essentially the square root of the determinant of the matrix. And then for, so this is for a planar graph, so, or a simply connected graph. And then for graphs embedded on higher genus surfaces, like say a torus, the full partition function is given by summing over all the different configurations of boundary conditions on that. So it corresponds to having a twist in your torus or whatever genus surface you have. So you're summing over the Pfaffians of those different Castellan orientations with a weighting of what's called an ARF invariant, which can be either +1 or -1. Yeah, so why do we do this? Well, for one, if we set beta equal to 0, all the bond activities simply become 1. So finding the partition function for beta is equal to 0 just corresponds to the number of dimer coverings on this graph. So that's how you can compute that there's 13 million ways of arranging dominoes on a chessboard. And you can, yeah, so you can get combinatorial quantities such as the number of domino tilings on an m by n rectangle. That was one of the earlier results obtained by Castellan. And then more interestingly, you can use the canonical partition function then to obtain thermodynamic quantities of these dimer models. So, and then these can be studied in further detail to observe things like phase transitions, which of course is always interesting to physicists. We're always trying to learn more about phase transitions. So yeah, let's start with the hexagonal lattice. So for the simplest case of a periodic hexagonal lattice, there are 3 different types of bonds. We've denoted them by the activities A, B, and C here. So this is what's called the fundamental tile of this. So if you were to repeat this tile around the entire lattice, you can build up the entire hexagonal lattice just from these tiles. And then the partition function is simply the sum over the coverings of A to the power of number of A-type dimers in your configuration, B to the power of number of B-type dimers, and C to the power of the number of C-type dimers. So that's how you compute your partition function for that. So this lattice is what's known as bipartite, which means that you can divide the graph into black and white vertices, such that black vertices are only connected to white vertices and white vertices are only connected to black vertices. So again, you can think back to that kind of chessboard type picture where a white square is only surrounded by black squares and black square is only surrounded by white squares. The Castellan matrix then of a bipartite lattice can be written in a special form, which is the following. So the A matrix here is an m by n matrix for a bipartite graph with 2 n vertices, and the A matrix can correspond to mapping from black to white vertices, is how we've defined it here. So considering a simple 2x2 case, 2x2 fundamental tiles of this hexagonal lattice, for doubly periodic boundary conditions, it looks like the following, and then computing the partition function by summing over the different twists in that toroidal structure, you get out that there's 9 total dimer configurations on this simple case. So what do these look like? So you can see we have 3 where they're all the same type of dimer, and then there are 6 configurations where they're mixed. So you can see here the different types of configurations. So in the top left, they're all just A-type dimers, then B-type dimers, C-type dimers, and then all the different mixings are at the lower end of it. So we're retaining the same thing that we would get from counting. So it's I suppose a nice verification that Castellan's theorem is working in that aspect. Okay, so in general, the doubly periodic A matrix can be written using the following. So where K1 and K2 are the x coordinates of the black and white vertices respectively, and the L1 and L2 are the y coordinates of the black and white vertices, respectively. So this matrix can be diagonalized using eigenvectors z to the k and w to the minus l, such that we get eigenvalues of the following form. So c minus a over z minus bw. This is what's known as the spectral polynomial then of this hexagonal lattice. So this is going to be quite important because we'll use this then to basically compute thermodynamic quantities in just a minute. Okay. Again, so using the fact that these indices are periodic, we're on a periodic lattice, then z to the power of n has to be 1 because, well, k plus n has to be equal to k for k1 or k2, and same case for w. So we can write them in the following form, where theta and phi are defined as laid out there: 2 pi n over n and 2 pi m over m. And then, so the determinant of A now just reduces to a product over these spectral polynomials, which is quite nice because then we can get what's known as the free energy per dimer, which is the logarithm of the partition function divided by the number of lattice sites, or sorry, the number of dimers, in the following way. So it just reduces to an integral over theta and phi divided by 4 pi squared of the natural log of these spectral polynomials. So once we have W, we can go ahead and compute our usual thermodynamic properties of the system. So Helmholtz free energy per dimer is simply minus 1 over beta times W. The internal energy per dimer is minus the derivative with respect to beta, and the specific heat capacity is the second derivative with respect to beta multiplied by beta squared. So for this hexagonal lattice, then when one of these weights A, B, or C is larger than some of the other two, we find that W is just the logarithm of that weight. And these are corresponding to what's called frozen regions. So in these cases, basically all of the dimers you'll have on your lattice will either be the maximum of those three weights. So if you have that C is bigger than A plus B, then your entire domain is just going to be taken up by these C type dimers, and same with B or A. So it's just the maximum of those three. So at the point where they're equal to each other, then there's a phase transition. So you can think of cooling it down, it kind of freezes into one of these states. So we want to see what this phase transition looks like then. So what I've done is I plotted these quantities for C is equal to 1 and A and B equal to e to the minus beta. So if you think of, okay, when is C going to be equal to A plus B? It should be at beta is equal to natural log of 2. We should see this type of phase transition. And indeed, you see at that point, it just kind of goes into that sort of frozen region here. So it's continuous for the Helmholtz free energy per dimer. It's also continuous for the internal energy per dimer. But when we look at the specific heat capacity, we can see a continuous or second order phase transition when approached from, so when you approach it from one side, it diverges, and in the low temperature regime, it's just totally flat, so it's not moving at all. And it's at 0 because C is equal to 1, so ln of C is just going to be 0. So it's a nice check to make sure that's correct. But yeah, so that's about it for the hexagonal lattice then. So moving on to the non-bipartite hexagonal lattice. So what do I mean by that? So we want to see what happens then when we introduce bonds between black vertices and white vertices, and see how this differs from the bipartite case. So we introduce these new bonds, make sure that our Castellan orientation is still intact. And again, we go about this kind of idea of setting up to observe these phase transitions and see what we can see. So we get that the determinant of the Castellan matrix takes the following form, where E in bold is denoting the E-type bond, and just regular E is just Euler's number. So it's a product over these determinants, and then the full integral for W in the continuum or thermodynamic limit looks like the following. So it's a bit messy. So what I did was I plotted it numerically to compute. So again, I just chose some parameters for C, D, and E being equal to 1, and then A and B equal to e to the minus beta. And again, I'm expecting that there should be a phase transition at beta is equal to natural log of 2. And so we'll see what happens. So Helmholtz free energy is again nothing overly interesting going on. I fitted it to a logarithm for to the following fit for what I'll explain it in a second why I've done that. Delta here in the fit parameters corresponds to beta minus beta C as well, I should just mention. Okay. And then same for the internal energy per diameter, there's no divergence or anything there, but when we look at the specific heat capacity here, we observe a logarithmic divergence, which is also symmetric about the critical point. So this is interesting because it implies Ising model-like behavior. So yeah, so as can be seen by the graph of that specific heat capacity, there is a continuous or second order phase transition at that critical point, logarithmic in nature and symmetric about it. And yeah, so this implies this in the same universality class as the Ising model. Yeah, basically. So by making the graph non-bipartite, we've now brought it into the realm of it being the same type of phase transition that's observed in the Ising model, which is interesting. Okay, so we see Ising-like behavior for one type of lattice that's non-bipartite. So I wanted to see if I could observe the same type of behavior for another non-bipartite lattice. So again, introduce another bond here to turn the previous lattice into a triangular one. So again, just denoting a new activity F for these dashed bonds here. So these are the new bonds that I've added in for this lattice. And play the same game of getting Castellan matrix, taking the determinant, which again is more complicated. So again, I plotted this numerically to see what type of phase transitions I could see, and we get something very similar to before. So now the phase transition occurs at, well, you see in a second, but I'm expecting the phase transition to occur at beta is equal to natural log of 3. And yeah, so again, nothing happened there. But then when you look at the specific heat capacity, there is indeed a logarithmic divergence that's symmetric about that point. So yeah, basically we're seeing Ising-like behavior again for this lattice at this critical point of beta is equal to natural log of 3. Okay. Yeah, so we've basically shown that these bipartite lattices kind of exhibit this Ising-like behavior, which is quite interesting. So now what I wanted to look at was what happens when you introduce a defect into these lattices, and yeah, basically see anything that pops out of that, any strange things. So we're going back to our original bipartite hexagonal lattice, but instead of having every bond of the same type have the same activity, we want to see what happens when we introduce a line of defects into this. So the way I've done this is by replacing the periodic A bond on the lattice with some defective A tilde activity. So again, visualizing this on a simple 2x2 fundamental tile case, you can see I've replaced the periodic A bonds with an A tilde activity. So we can kind of play around with this and see what the partition function looks like. So it looks like the following. So you basically replace one of those A bonds with an A tilde, and different values of A tilde then have different meanings. So if we say set A tilde equal to minus A, then it corresponds to having anti-periodic boundary conditions instead of periodic ones. If we set A tilde to 0, you can think of it as snipping the bond, or having, instead of having your lattice on a torus, you have it on a cylinder now. So you have periodic in one direction and then no periodic boundary conditions in the other direction. And now I'm still working this out, and hopefully it'll all be in the report in full detail, but I found some non-trivial consequences for the partition function, such as it being negative valued or even 0 valued, which is quite interesting. So yeah, hopefully we'll see where that leads, and that'll all be in the report as well. Okay, so just to wrap it up then, I suppose, is so dimer models are interesting as an exactly solvable model because it can teach us about phase transitions and other phenomena in physics and mathematics. Dimer models on non-bipartite lattices tend to show Ising-like behavior, showing a continuous or second order phase transition that is symmetric about the critical point and logarithmic in nature. And defects on these lattices can seem to lead to non-trivial consequences for partition function and henceforth the thermodynamic properties of these lattices as well. Yeah, so I just want to say thanks as well to Dias for the opportunity to do this project. It's been really enjoyable, the time I spent here. In particular, I want to thank Professor Denjo for helping me out. He was always very receptive whenever I walked into his office asking him questions, and of course Dimitri and Sabine as well. So yeah, just want to say I really enjoyed my time here and open to any questions as well. Any questions? Yeah.
How do you go about interpreting a negative partition function?
That's a good question. So there was a paper by Seiberg and Shao on this kind of idea on what's known as a Majorana chain. So they introduced some strange defect into that and got some weird stuff with the partition function happening. And it's related to non-invertible symmetries on it. Now I'm still digging into the details of it, but yeah, that's kind of one interpretation of it. It's also like having a negative partition function in that regard, like we've introduced kind of a negative activity, which you can also think is sort of an unphysical thing to do usually. So yeah, I'm not sure 100% what the physical interpretation of that would be, but I will dig into it and you can read the report to see my final verdict on it, I suppose. Yeah.
So you say you identify that it's the same universality class as the Ising model?
Yeah.
So what you used to have in terms of like, is there something you can identify that the Ising model is not this model? That's why it's useful to identify that it's the same universality class.
Sorry, what do you mean by
So as in terms of sort of like you're saying it's similar to the Ising model in some way.
Yeah.
In what ways is it similar?
Yeah.
You obviously know how the Ising model behaves for certain.
Yeah, it's that idea of in the Ising model you see a similar type of thing where there's a second order phase transition where you see nothing overly strange happening with the Helmholtz free energy or the internal energy, but then when you look at the specific E capacity, you see that logarithmic divergence that's symmetric about the critical point. So that's the thing that places it in the same universality class as the Ising model, I believe.
So is there any other properties that things in the same universality class share?
There is, which I haven't fully dug into yet. I'm hopefully going to include some more stuff in the report. So, but yeah, I'll let you know. Any other questions? Yeah.
And in your driver last example where you have this capacity, it's kind of just difference between is that just numerical error?
It is, yeah, I think that's just numerical error, yeah. Again, I'm hopefully going to try and clean that up and get it nicer for the report, but yeah, that was the last simulation I ran basically before today. So yeah, we'll see if I can. I'm fairly sure it's just numerics that's leading to that issue as well. Yeah. Okay.
Great, so let's